In this example, I'd like to use the method of virtual work to approximately determine the deflection of a simply supported beam with a point load acting in the center of it. So the space of solutions for this problem consists of deflections v of x that take on values 0 at x equals 0 and x equals L. So we're measuring x from the left-hand side there as usual. And the space of test functions that's appropriate to this problem is ones that have test functions that are 0 at 0 and L. So our usual notion of kinematically admissible test functions or variations. And the expression, the virtual work equation for this, or theorem, says that the external virtual work, so minus P del V at L, so the minus sign because the force is going downwards, is equal to the internal virtual work, which is the integral from 0 to L of the moment, which is a function of x, times the virtual motion. So that's two derivatives of it, sorry, so the curvature there, so the virtual curvature. And what I'm going to do is look at an approximate solution. So I'm going to construct a subspace of S, we'll call it S tilde, and it's going to be a set of functions v such that v is equal to a times x times L minus x. So it's a very simple quadratic function that satisfies my kinematic boundary conditions. And for the space of test functions, I'll choose test functions of the exact same form. So del v is equal to del a x times L minus x. So this is the Bubnov-Galerkin methodology here. So, and the way this works now is that we'll plug in our approximations for S tilde and V tilde. So this is proper subset of S, proper subset of V. We'll plug those into the virtual work equation here, and we can use that to determine what A is in this. We'll get a particular function out of the set S tilde. And the way we do this is just simply plug in the functional form. So we have minus P del A L squared over 4. So if we evaluate del V at x equals L, that's what we get. And then on the other side, we have our integral 0 to L. The moment itself in an elastic beam, remember the moment is EI times kappa, the curvature, so the second derivative of the deflection. So this becomes EI times A minus 2 times del A minus 2 dx. So on this side of the equation here, we get 4, if we do the integral 4 EI A L del A. And so this relationship here has to hold true for all del A's because the virtual work expression has to hold true for all virtual motions, so that includes all del A. So we can go ahead and solve then for A. A is equal to minus PL over 16 EI, and that leads then to an approximate solution. V of x is equal to minus PL over 16 EI x times L minus x. So that gives me my approximate motion to the system. In this problem, we happen to know what the center deflection is. It's a simple problem to solve, say, with a differential equation. So the center deflection is PL cubed over 48 EI, so we could evaluate this and determine the error. So if we look at our approximate and evaluate it L over 2, what we'll find is that we get minus PL cubed over 64 EI. The exact solution in this particular case happens to be minus PL cubed over 48 EI. So this is roughly, well, in this case, at this point, it's certainly a 25% error. So the approximation is only modestly useful, but this illustrates the idea of how one can construct an approximate solution using the method of virtual work. If we had picked a more complicated subset S tilde or V tilde, then we could have got a much better answer.